Hello, welcome to this video. In this video, we will solve few numericals on steady flow energy equation, or we can say that numericals on first law of thermodynamics for an open system. So let us start with the problem. A turbine operating under a steady flow condition. So this is a hint that he is talking about a steady flow device. A turbine operating under a steady flow conditions. So you can say there is a turbine. We generally denote it with this kind of a symbol for a turbine. So, and there is steady flow. So, it is a steady flow device. So, receives 4500 kilojoules of steam per hour. So, mass flow rate is given 4500 kg per hour. So, this has to be in kg per second. So, we will convert this as soon as we get this data 4500 divided by for hour we have 60 minutes and 60 seconds. So, now this will be in kg per second. 4500 divided by 60 into 60. So, that is 1.25 kg per second. So, mass flow rate is given as 1.25 kg per second. See, the unit need not to be given in the unit which we want. We will have to convert it to the unit which we want. Okay. The steam enters the turbine at a velocity. So, velocity is given. So, entry we have always said it as 1 and exit as 2. So, steam enters the turbine with a velocity of, so capital V1 indicates velocity 2500 meters per minute. So, we will convert this into meter per second again. So, minute is in the denominator. So, how do we convert minute to second? 60 seconds. 1 minute is 60 seconds. So, this will be meter per second. Now, again we will convert this 2500 divided by 60, which is 41.6. 41.6 meter per second at an elevation of 4 meters. So, remember we had said that the elevation which we denoted by the symbol Z1 and the outlet elevation was given as Z2. So, anyhow, so elevation at the inlet is given as 4 meter. So, Z1 is 4 meter. Specific enthalpy of steam. So, H1 is also given 2751 kilojoule per kg, but we want it to be in joule per kg. So, 10 power 3 joule per kg. Now, he is talking about outlet. It leaves the turbine. So, at a velocity of 9.33. So, outlet data I am writing it here 9.33 meter per second at an elevation of 1 meter. So, Z2 is 1 meter. So, I can change the diagram if you wish to, but the meaning is Z2 is little lesser. Z2 is just 1 meter, whereas Z1 was 4 meter. Alright. And a specific enthalpy at outlet is 2266 and in kilojoule per kg, but we will have to convert that into joule per kg. Okay. The heat loss from the turbine to the surrounding. So, heat from the turbine is lost. Of course, we had assumed it as a device with a perfect insulation or adiabatic, but here he is giving you that there is a heat loss from the turbine to the surrounding. So, there is a Q. Alright. So, this Q is giving you, this Q is 16,800 kilojoule per hour. Now, remember this has to be minus because negative because heat is lost. This comes from the sign convention, negative because heat is lost. So, whenever heat is lost or heat is rejected from the system, it is negative. Negative because heat is lost. Okay, but the unit again, it has to be kilowatt. So I will divide this by 3600 or 60 into 60, 60 minutes, 60 seconds, which will be 3600. So kilojoule per second. That will be 16,800 divided by 3,600. 4.6 kilowatt. Or we can say 4.6 into 10 power 3 watts. Or 4.6 into 10 power 3 watt means joule per second. Okay. So determine the power output. So he is asking you the work transfer and is interested in kilowatt. W should be written in kilowatt. Now we already know how to write the equation of steady flow energy equation or first law for an open system. So let us start from there. The simplest form is Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. Okay. Now Q is, we have already found out, this is minus by the way. So minus 4.6 into 10 power 3. Now unit has to be balanced. This is in joule per second. So then work transfer will be definitely coming in joule per second. Because you are substituting this in joule per second, work transfer is expected to be coming in joule per second. And enthalpy should be in joule per second. So this has to be multiplied by mass flow rate m dot into H2 minus H1. You can check now. If you substitute mass in kg per second and enthalpy in joule per kg, this will be in joule per second. Plus change in kinetic energy is half into m v square, that is v2 square minus v1 square. Now again here, so plus half into m dot v2 square minus v1 square plus m dot g into z2 minus z1. We can check the unit here. Mass flow rate is in kg per second and this in meter square per second square, which is joule per kg, which we have already proved in the last class. Meter square per second square, joule per kg and meter square per second square, both are one and the same. You can refer to the last video. So this kg goes off and you will have joule per second again, watt here. Again here kg per second. Acceleration due to gravity is meter per second square and this z will be in meter. So this is meter square per second square. So meter square per second square is nothing but joule per kg. So this whole term is joule per kg again. Kg goes off, joule per second. So the unit has to be appropriate. Otherwise we'll get the wrong answer. Now let us substitute minus 4.6 into 10 power 3 minus work transfer, which we have to get it in joule per second, must be equal to mass flow rate is 1.25 H2 minus H1. So we can take common, otherwise we'll write it 2751 into 10 power 3 minus H2 is 2266 into 10 power 3 minus 2751 into 10 power 3. This is our H2 minus H1 plus half into 1.25 into velocity square 9.33 square minus V1 is 41.6 square plus 1.25 into 9.81 into Z2 minus Z1, that is 1 minus 4. 1 minus 4. Now let us solve this equation one by one. Let us take this as our first term, this as second term and this as third term, and we'll try to write it separately because we don't want to make any mistake. Okay. So this will be 1.25 into 2266 into 10 power 3 minus 2751 into 10 power 3 . So that will be the first term will be minus 606.25 into 10 power 3. This is our first term plus this half into 1.25 into 9.33 square minus 41.6 square. So second term is, so this is minus 1027.19 plus the other term is 1.25 into 9.81 into 1 minus 4. So minus 36.78. Minus 36.78. Now on the other side we have minus 4.6 into 10 power 3 minus W. Now the only unknown is W, we must be able to get it. So let us do this. Minus 4.6 into 10 power 3. Now minus the unknown, I am gonna write it as alpha x. Now alpha equals minus, that is, I will open a bracket, minus 606.25 into 10 raised to 3 minus 1027.19 minus 36.78. Now we can shift solve for x is equal to 0. We have this answer which is 602.7 into 10 power 3. Now this W which we are getting watts, or we can say work transfer or power in kilowatt is, divide this by 1000 in order to get it, divide by 1000 to get it in kilowatt. So if you divide that by 10 power 3 or 1000, this 10 power 3 goes off, you will have it in kilowatt. So since it is a power producing device which is a turbine, obviously the work transfer should be positive, and we can say that the power produced by this turbine with this data is 602.7 kilowatt. Thank you.